So the expression that we had arrived at yesterday is that for any scalar variable, it can be scalar, vector, doesn't matter. The total derivative is equal to the local temporal derivative plus u del phi del x plus v del phi del y plus w del phi del z. And equivalently, in a vector notation, this was written as u dot nabla operating on phi. In an Einstein notation, this can also be written as del phi del t plus ui del xi of phi. So this implies a summation, and I hope it is clear how it is going on. So in this summation notation, u1, u2, u3 are the three velocity components, x1, x2, x3 are the three spatial components. Anyway, so we can then write this down as del phi del t plus now u dot nabla, this operator over a certain line. So if this line is the direction of the velocity also, then u dot nabla represents the magnitude of this velocity and the gradient is along this particular line, because we know that the particle is being transported over this line. Okay, so this is the imaginary line on which the particle is traveling. So u dot nabla is equal to the magnitude of velocity along this line, and the direction of the gradient is along this tangential to the particular line. So if I call it as a ds, not vector, so let me call this change as ds. So this will be mod u times del s. The dot has vanished because we know that the direction is along ds. The direction of the gradient is along ds, and this, anyone who is conversant with a bit of vector calculus can easily identify this. Let us proceed to methods of flow visualization. And this will not cover experimental methods but mathematical techniques for flow visualizations. So the first and most important is a streamline. What happened? What happened? I am doing the recording on my PC locally. I am not doing it using Teams. And this is what has been going on for all the lectures. So I don't think you have to restart because. Okay, so first of all these lectures will be going up on television on DTH channel. So I will edit together many of these clips. So I request you not to interrupt right in middle of something. You can, of course, I'll prompt you when you can ask. Okay. So let us proceed to visualize. Rather, let us proceed to look at some mathematical techniques to visualize flows. Or rather, it's how we can describe flows in this particular framework. So in the Eulerian description, we know that given a domain, we have information about the fluid velocity at all different points in the domain. That is, the velocity is actually a field variable. So at all the spatial points in the domain, I know the information about the velocity, all its components, and how they will evolve in time. So at a given snapshot, if I take at a given time, I take a snapshot of the velocity, I will say have something like this. So the streamline is a line which is tangential to all the velocity vectors. And the meaning of something being tangential to all the velocity vectors, let us try to put it in mathematical terms. So suppose I have a velocity vector like this. I can call it v, I can call it u, doesn't matter. So if I want to find the equation of a line, suppose this is that line, okay, I want to find out the equation of this particular line. So at this particular point, I can say that the ds vector at this particular point, that is the increment of the displacement along this particular curve at this particular point. So ds vector should be parallel to the u vector, because streamline is by definition the line which is parallel to the velocity vectors. And so if this is true, I can write u cross ds to be equal to 0, because they are locally parallel. By locally parallel, I mean to say at this point I have drawn the curve like this, but the curve would be like this if velocity at this point would be something like this. If I know that the velocity over here is something like this, the velocity over here is something like this, the velocity over here is something like this, then the curve in question, that is the streamline, would look something like this. Something like this. So that at all points, it is the increment in the displacement vector along the streamline would be parallel to the velocity vector at that point. So this is the mathematical condition. Let us try to write it down for simple Cartesian coordinates using the good old rules of cross products. So ds component, any displacement ds will have components dx, dy and dz. So essentially ds vector is dxi plus dyj plus dzk, and we must understand that dx, dy and dz are not independent, because I cannot vary dx by a certain amount and dy by only this amount. In order for me to lie on this particular curve, dy must necessarily be this quantity. So dx, dy and dz are such that we will always lie on the curve, which satisfies this particular constraint. So let us proceed with the cross product. It will be this. So the I component is v dz minus w dy. The j component is going to be w dx minus u dz, and the k component is going to be u dy minus v dx. And because each of these components has to be 0, because the cross product is a 0 vector, so this implies that v dz minus w dy is equal to 0, w dx minus u dz is equal to 0, and u dy minus v dx is equal to 0. From this, we can conclude that u upon dx is equal to v upon dy is equal to w upon dz. And this gives us a parametric representation of what? The equation of the streamline at a given time instant is going to be. It is important to note that a streamline is not a time dependent quantity, meaning I will always define a streamline at a given time instant. So in order to specify how a streamline looks, I must also specify at which time instant I want to look at a flow. Flows can be of different kinds. We can have steady flow, we can have unsteady flow, we can have uniform flow, and we can have non-uniform flow. The two quantities over here refer to whether the flow changes in time or not. And the two quantities over here, they refer to whether the flow is constant all over space or not. Let us consider some hypothetical flows which will reinforce what the various kinds of flows are. So a steady flow. So let us consider a steady and a uniform. So let us consider a flow which is steady but uniform. So it could be, suppose I draw this particular domain, and suppose the velocity is something like this. I'm showing the velocity with the help of these vectors. And these velocity vectors do not change in time. So in this case, the flow is uniform in the x direction, the flow is uniform in the y direction, and the flow is steady. What about this particular case? The flow is parabolic, meaning the velocity near the top and the bottom walls are 0 and the velocity is maximum near the center line. So this particular, suppose this flow profile does not change over time, meaning whatever we see at this particular time instant will be the same velocity at all subsequent time instances. So this flow is steady, but the flow is non-uniform in the y direction. But the flow is uniform in the x direction. So let us look at some more drastic examples of steady but non-uniform flow. We can have a diverging section, that is flow comes in through this point and the flow diverges. So this particular flow is not changing over time, meaning the inlet conditions are kept fixed, the outlet conditions are also kept fixed. So this flow profile does not change over time, and this flow is both steady and non-uniform. Let us look at some examples of unsteady but uniform flows. So let us draw the flow profile as something like this. It's uniform, so all the velocity vectors must be in the same direction throughout the flow domain. And if this is the snapshot at t equal to 0, at some other time instant, I can have a reversal of the velocity such that all the velocity magnitudes are uniform over the space and they point in the same direction. So over t equal to 0 and t equal to 10, suppose the velocity is still uniform, but the direction has changed. So it has gone from pointing towards the right to pointing towards the left, and so this is a case of unsteady flow but a flow which is uniform. And lastly, the most general case, a flow which is both unsteady and non-uniform. So in this case, we can look at this particular flow domain, and instead of having uniform flow coming in which is not changing over time, I can have a flow which changes over time. So let the inlet flow at this particular time instant look something like this, but the inlet flow at a certain other time instant may be in the opposite direction. So I could have a flow something like this, and this would cause an alteration in the flow. The flow would no longer point from left to right, but the flow would in fact point from right to left. The flow would be something like this. So the flow is both non-uniform in space and unsteady in time. So any questions so far? Any questions? Okay, let's continue. The other way of visualizing a flow is quite simple. It's called as a path line. In order to find out the path line, if we have a given flow domain, there is some flow domain, suppose it's something like this. We will inject one particle into the domain. It can be a hypothetical particle, or it can be something which is neutrally buoyant. So neutrally buoyant particle means a particle which is not affected by the difference in density between the fluid and the particle, and we will track the motion of the particle as it goes through the flow. So this is a Lagrangian tracking technique. Why does the particle need to be neutrally buoyant? So suppose the flow is happening like this, and this is the z direction and this is the x direction. So gravity acts along negative z direction. So if the particle is not neutrally buoyant, if the particle is lighter than the fluid, then the particle will have a net force acting like this. So during its conveyance in the flow, the particle will not follow exactly the path of the flow, but it will shift across different streamlines. So if you can imagine, at a given time instant, a streamline is like this, like this, like this. So these are the streamlines. Any particle which originates over here will remain confined to a streamline if the flow is steady. So the particle will travel along a streamline. But if the particle has a net buoyancy force, then the particle will go to a different streamline. After a while, the particle will go to a different streamline, and so on. So despite the streamline being something like this, the particle trajectory will be something like this. So the particle trajectory and the actual flow direction will deviate. Hence, we want that the particle not experience any net force in any direction. So the particle has to be both small, because if the particle is not small, the particle will experience a net drag force. So it will not exactly move with the flow, it will move with a retardation with respect to the flow. So particle has to be both small and the particle has to be neutrally buoyant. This example that I said, that the particle will move on a streamline, I said that this is true for a steady flow. But in any unsteady flow, it may not be the general case, because the particle, suppose that the flow is unsteady, the particle at t equal to 0 is over here, and let's say at t equal to 0, the snapshot of the velocity fields gives us these streamlines. So at t equal to 0, the particle wants to go in this general direction. So the particle will end up over here after a small time. But say that the unsteady flow changes its direction from this particular streamline to something like this. Let me draw it with a red color. So at the next time instant, the red color shows the streamlines at the times at the snapshot at t equal to t1. So this is the particle at t equal to t1. This is the particle at t equal to t naught. The white is the streamlines at t equal to t naught. So after moving to a point over here at t equal to t1, it will see that the velocity at this point will be something like this. So then the particle will take a trajectory over here. So the trajectory will look something like this. So the path line and the streamline are significantly different when the flow is unsteady. The path line and the streamline are identical when the flow is steady. Now we've said that we put a hypothetical particle in the flow and we evolve the particle in the flow field. Let us put this in mathematical terms. So the velocity of the particle sampled at a given point, so it will sample the velocity of the flow, because we are assuming that it is a neutrally buoyant particle and a small particle, so that the presence of that hypothetical particle or even a real particle does not affect the flow. If we have a large ball in the flow itself will get affected and we will not truly get how the velocity field looks like. So under these assumptions, the velocity that the particle will sample, it will be the UVW velocity at the particle location. So at this particle location, U will be dx dt of the particle, so I will call it P. V will be dy dt of the particle, and W will be the dz dt of the particle. So UVW sampled at the particle location. So let me define the particle location as the x vector P. X vector P stands for x particle, y particle, z particle. And of course, these are ordinary differential equations, so I must supplement these equations with appropriate initial conditions. So at t equal to 0, I must say that the location of the particle at t equal to 0 is some xp naught, yp naught and zp naught. So the particle originates somewhere over here. So this is xp naught. It samples the local velocity, then it moves over here. Again it samples the local velocity, let me call it xp1. Then it samples the local velocity at this point. So the local velocity at this point can change over time for an unsteady flow. It may not remain constant. But the fact is, I am sampling the unsteady velocity at the new particle position and not at the old particle position. So I am sort of sampling the velocities prevalent at the point in concern. So suppose the particle is over here, I am sampling the velocity at the particular point in concern at the time it takes for the particle to reach this particular point. Okay, so at this particular point, if the velocity is like this, the particle ends up over here, say. Then if the particle is some velocity sampled is something like this, it goes over here. Then it samples a particle something like a velocity something like this, it goes over here, and so on. So it is simply finding out the trajectory of a particle, which is nothing but tantamount to doing the same thing in classical mechanics as finding out the Lagrangian statistics. So this is a very easy way of finding out velocities, for example, in the oceans. So the ocean, I'm drawing the top view of an ocean, just a small section of the ocean. So you might have seen that in the ocean they put neutrally buoyant buoys. So these buoys are designed in such a manner that they experience no net force in the vertical or the horizontal direction. That is, the buoys don't drown or something. They always tend to remain at the surface. The buoys are much smaller. The buoys are quite smaller as compared to the length scale of oceanic flows. So when I say that a neutrally buoyant particle has to be small, it has to be small with respect to the flow. So the flow, you know that the ocean velocities, the gradients in the ocean velocities can span over several hundred meters. So the buoys are typically much smaller than the length scale over which the gradient in oceans happen. Okay. So these are the ocean currents at the surface. And because of this, the buoys will be transported along the direction of the flow. Okay. Because of this, the buoys will be transported along the direction of the flow, and that is how we can find out the surface velocity at the ocean. An example of something which is not a neutrally buoyant particle, but it was very important for us to track, was the disappearance of the aircraft MH370. The fragments of the aircraft were eventually found quite far from what was suspected to be the site of the crash. It was expected that it was somewhere near the South Asia Sea. So eventually it was found somewhere near the east coast of Africa. So the fragments, when they fell into the ocean, the fragments then, because they are not neutrally buoyant, they started sinking towards the sea. So if I draw the cross section of the ocean, so the fragment starts to sink towards the sea, and it samples different velocities as it goes towards deeper depth. So it is not neutrally buoyant. It will not be the same velocity as the surface velocity of the ocean, and it will sample different velocities as it is crossing different depths. Moreover, the velocities in the oceans are all time dependent. So at a time instant, you may see that the velocity is something like this. So you may think that a debris particle that may fall over here will travel like this. But no, at some other time instant, the velocity might change and become something like this. So the debris particle will initially move like this, then it will move something like this. Then after another time instant, the velocity may become something like this. So the debris particle will move something like this. So it is not entirely easy for us to determine with only a time snapshot what the particle motion will be. We have to look over entire history of how the particle has sampled all the different velocities in order to find the trajectory of a particle. These ideas would be more reinforced with the help of certain examples. But all I want to say is such kinds of particle trackings are quite important for various exploration missions. The last method of visualization is called as a streak line, and a streak line can be assumed to be a natural extension to that of a path line. Let us first uh, imagine that we have a flow in a domain something like this. Okay, there's a flow in the domain. The flow can be unsteady, no problem. How do I typically visualize flows? What do we do is we put a dye inside the flow. So we take a syringe. So if it's water, we take a syringe, and at this point we push a certain colored dye in the flow. So because of the pushing of a colored dye, the colored dye will be sort of taken with the flow. So I will see, if the dye color is yellow, I will see a line in the flow. So this is how we visualize flows in liquids. If it is air, if I want to visualize the flow in air, I will take smoke and I will try to inject smoke at a point. So smoke will come out and it will show us the direction of the flow. If the flow is unsteady, then the smoke will also go to different directions. But now, what is really happening? When I say that I am injecting colored dye and I am observing how the dye looks like in the flow, what am I really looking at? So let us say I inject a dye at this particular point, and at t equal to 0 to t equal to 1 second, the flow is in the x direction. So the dye, all the particles in the dye will be transported in this direction. Suppose I say that the velocity is 1 centimeter per second. So the length of the dye column will become 1 centimeter at the end of 1 second. So this is the point of injection. Let's say that at t equal to 1 to t equal to 3 seconds, there is a velocity which is in the y direction. So in that case, this dye will move upwards. This dye will start moving upwards, but at the same time there is new dye continuously being injected at this point. So there will be a tail like this also. So this is how the dye would look at t equal to 3 seconds. Meaning I am keeping the injection point fixed. Mathematically what is going on is I am keeping the injection point fixed. I am successively injecting dyes at that particular point. And I am sort of looking at the locus of all the dye particles. Let us magnify the drawing and try to arrive at a much easier viewpoint. So suppose this is the domain and this is the needle of the injection. So at t equal to 0 seconds, suppose a dye particle comes out like this and the flow is in this direction. Now at t equal to 1 second, the dye particle, the red dye particle will arrive at this particular point, but another dye particle will be injected into the domain. So this is at t equal to 1. At t equal to 2, suppose the velocity is unsteady and the velocity direction is something like this. Then this red particle would move over here. This orange particle will also move over here. And there would be a new particle which would be coming out at this. So at t equal to 2 seconds, what is the locus of the dye particles that I see? That locus will be this particular line. So this is how I would visualize the flow to be. Now suppose the flow changes velocity and it is something like this. Then this particular red particle will end up over here. This particular red particle would end up over here. Let me erase this particular red particle. This particular particle would end up over here and there would be a new particle coming in over here. So at t equal to 3, the trajectory, the locus of all the points that I will see would be this. So it would seem as if the die has taken this shape. Now suppose at the next time instant the velocity is something like this. The velocity is again something like this. Then this particle would end up over here. This particle would end up over here. Let me rub the t equal to 2 lines. This particle would end up over here. This particle would end up over here. This particle would say end up over here. And there would be a new particle coming in. So this is at t equal to 5. So the locus of all the particles at t equal to 5 would be something like this. So this is the die that you would see. So streak line is the locus of all particles injected at a given point, at a fixed point, at all successive times So this is basically what a streak line is. Now let us see whether a streak line and path line can coincide. Whether a streak line and path line can coincide. Basically what is going on is, if I want to visualize the streak line at t equal to 5, I must inject various particles into the flow domain from t equal to 0 to t equal to 5 at a fixed point. So in order to find the position of this particle, I must sort of obtain the path line for this location. So for this particular point, the path line can be significantly different from the streak line. So the path taken by the first particle could be something like this. But at t equal to 5 seconds, this particle has arrived at this point. For this point, the path line for this particle could be something like this. Meaning, this particle was injected 4 seconds prior to the arrival at this point, at this particular point. So if I inject a particle over here at t equal to 1, at t equal to 5 seconds, it would arrive over here. That is, for this particle to arrive from this, it has taken a time of 4 seconds. For this particle to arrive from here to here, it has taken 3 seconds. And suppose this is the path taken by this particle. For this particle, it has taken 2 seconds, and this is the path taken by this particle. And for this particle to arrive, it has taken 1 second, and this could be the path taken by this particle. And this particle is already at the origin. So the path line for each particle is different because the flow is unsteady. But I cannot really visualize a path line. I can only hypothetically visualize a path line. But I can surely visualize the locus of all the particles, because all the particles will have certain color. So if there is a series of particles I have drawn particles quite separated, but in general the injection will be almost continuous, and so I will see a series of colored particles, and that is the locus that I will see. So I will see a color, a streak of color. Okay, so I must find out the path line for each particle, let it all converge to a certain time at which I want the streak line. The important thing is, for all the different particles, the location of injection is the same, but the initial times are different, meaning the initial condition for this was 5 seconds earlier to this snapshot. The initial condition for this was 4 seconds earlier to the snapshot. The initial condition for this was 3 seconds prior to the snapshot. For this, 2 seconds prior to the snapshot. For this, 1 seconds prior to the snapshot. And for this, it is at the instant of the snapshot, that is 0 second at the snapshot. So times are all successive. This is what we mean by successive times. So when can a streak line and path line be same? If I have a uniform flow, then I know that a particle injected in the domain, so suppose this is the point of injection, the particle will always keep moving along this line. In fact, if the velocity is steady, this line itself is also the streamline. So particle 1 will move on this line. So suppose at the end of 5 seconds, particle 1 has reached over here. So this is the first particle that was injected in the domain. This is at t equal to 5 seconds. The second particle, which would have been injected 1 second after the injection of particle 1, would reach some distance over here. So this is second particle at t equal to 5, but it was injected at 1 second. This was injected at 0 seconds. Then the third particle at t equal to 5 would be over here, but it was injected at t equal to 2 seconds, and so on. So all the particles which are injected at this particular point would necessarily lie on this particular streamline, because the flow is assumed to be steady. And if they are lying on the same streamline, the locus of all the points injected from this particular point at all successive times prior to the snapshot will also lie on this particular line, and hence this is going to be the streak line. The red colored line is going to be the streak line. As time advances, the streak line will become larger, but it will still coincide with the streamline and all the path lines. So for a steady flow, the streak line lies on the streamline, and the path lines also lie on the streamline. So for a steady flow only, streamline, streak line and path line are all identical. For any unsteadiness in the flow, everything will change. The particle trajectory would be different from the streamline, because the streamline would be at different time snaps. The particle trajectory would be different because you are sort of sampling the particle trajectory at a given location of the particle at the prevalent velocity fields. The streak line would successively be the locus of all such path lines, of all such particles that we have in the flow domain. Okay, so any questions so far? Conceptually, do you have any question? What is going on?
Sir, how can streak line and path line be different?
So let us see how. So let us see just a path line. So suppose you have a flow in this direction at 1 meter per second for time period of 2 seconds. So let us draw, and then after, at the end of 2 seconds, for 3 seconds we will have a flow which will be 1.5 meter per second in this direction. So let us see how the path line for a particle originating at t equal to 0 would be. So 1 meter per second for 2 seconds. So the particle will travel 2 meters, and then for the next time instant it will travel 4.5 meters. So this is the path line of the particle injected into the domain at t equal to 0 given this flow profile. But see, now let us inject a bunch of particles successively at this particular point. All the particles are now, so let us see, for 2 seconds all the particles are injected at this particular point for 2 seconds. So all the particles will move along this line. So the last particle, so at t equal to 2 seconds, this particle just coming out from this injection point would be the particle. This particle would be, so this particle would be the oldest particle in the domain. This particle would have been injected at a 2 second interval. So at all previous times, the particles would lie over here. Do you agree with this?
Yes, sir.
Now the velocity would become 1 and 1.5 meter per second for the next 3 seconds. Now the moment I have a 1.5 meter per second velocity, all the particles will start to move in this direction. So all the particles would move 1.5 meters over here. Not only that, but the last particle that was coming out, that particle will move at the same y location of the injection point to over here. But even after 2 seconds there is an injection going on, so all the new particles which are injected after 2 seconds will also lie on this line. So the locus of all the points that I will see is this. So the path line for the first particle is this, but the streak line would be this. Is it clear?
Okay, sir.
Just to put into perspective, the first particle was injected. This particle, the very oldest particle, has now entered into the flow domain for a total time of 5 seconds. All these particular points were successively injected at this point. So the residence time of this particle inside the domain would be less than 5. The residence time of this particle would be less than whatever the residence time of this is. And this particle is just introduced into the domain. Just. So what would be the residence time for this particular particle? That particular particle had entered into the domain at t equal to 2 seconds. So this particular particle, which is at the same level at the point of injection, after which all the particles are at a different y location. So this particle would have been injected into the domain at 2 seconds after the first injection, that is 3 seconds before this particle was injected. So 3 seconds before this, so 3 seconds before this, it would have been at this point. This particular point would have been at this point 3 seconds. After 3 seconds, this whatever this point is has traveled from this point to this point, and there is a new particle which originates over here. So all these particles have a residence time of larger than 2 seconds but less than 5 seconds. And this particular point has a residence time of 0 seconds, that is, it has just entered into the domain. So the streak line is this, while each particle has a different path line. The path line for, suppose I want to know the path line for this particle, the path line for this particle would be this particular curve, because this is how the trajectory of this particle would have looked. Okay, this particle would move up, but because it was injected after a certain time before 2 seconds, so it moved slightly up. Then it sees that this flow has changed from 1 meter per second up to 1.5 meter second towards the right, and thus it has traveled like this. So it has not seen the entirety of the 2 seconds of the 1 meter per second flow. It has seen only a part of it. Suppose it has seen only 0.5 second of it. Is it clear by this?
Yes, sir. Clear.
So we cannot visualize path lines directly. We can only visualize the locus of all the points. And so we must know the path lines to understand where at a given time instant all the particles lie in the domain, and then the locus of all these endpoints of the particles is what the locus is, and that is what we will visualize as a color, as a fluorescent dye, or whatever. Okay, so any doubts in whatever we have discussed so far? William, is it clear?